Hello everybody and welcome to NPTEL online certification course on cryogenic electronics for quantum computing. This is lecture number 49 and from henceforth onwards we will be deep diving into qubits and how qubits are manipulated by the electronic readout circuitry. So the outlines of this lecture is we will be looking into what is a qubit and how qubits and the bits is basically the binary digits which we are talking about, which is conventional electronics, digital electronics, that we will see a difference between the two. We will be also looking into the facts that how qubits are represented in a mathematical sense of it. Then we will look into the bits versus qubits, how it is used in processors, and then realization and applications of qubits. So this is the general scheme or the outline of the talk which we will be doing, right? So let's see what the qubits are. So if you look at the qubit, a bit is of course the smallest unit of any classical information, right? So basically if you look from your digital electronics course from your first year level bachelor's UG program, you will see that a bit is basically the smallest unit of classical information and they are represented either as a 0 or a 1. We all know this. 0 is off state. In Boolean expression they are expressed as false, and in potential form they are expected as low voltage, whereas 1 is represented as on and it is a true value in Boolean and it is a high voltage. So at any particular node in digital logic, if a node is having a high voltage, it is represented as 1, and if it is a low voltage, it is represented as 0, right. So this is the positive logic which we are talking about here, that high is equivalent to 1, low is equivalent to 0. You can also have a negative logic where 0 is represented by high voltage and 1 is represented by a low voltage. So basically there are only two possible states with conventional bits which we have, right. So if you look at the diagram on the right hand side, so if you look here in this diagram here, the presence or absence of potential is referred to as a bit, right. So there are, say, these are how many bits? This is 7, this is 4 and this is 4. So there are 8 classical bits available and these bits are represented as 1 1 0 0 1 0 0 1. The last one is missing here, there will be a 1 and this corresponds to 1 here. However, a qubit is the quantum version of a bit. So a qubit can actually be, it can be 0 as well as 1, right. So it can be either 0 or can be read as 1, and this is where principle of superposition comes into picture, that you can also have a combination of 0 and 1 at the same instant of time with appropriate weight attached to it. Now in quantum computing we define the qubit or a quantum bit, we define qubit, right, and it is also referred to as a quantum bit, is the basic unit of this is the basic unit of quantum information, right, and bit is basically two states, either 1 or 0 it can have in the simple 2 level quantum mechanical system, and it all displays the peculiarities or the tendencies of a pure quantum mechanical picture which we have. So as an analogy you can say it like spinning of a coin. If you spin the coin you can either have heads or tails, right, but when it is spinning you are not very sure about the outcome of the coin, but when it stops then you are very much sure that this it's a heads or a tails available, but when it is spinning we are not very sure about the type of output which you will get. Now the qubit concept was first introduced in terms of, if you look at etymology, how to name it actually, then it was first named in qubit by Benjamin, right, and this was done in 1995 was the first term when Benjamin Schumacher was the first person to name it as a qubit, right, and he named it as a qubit. So let us now look at the difference between a bit and a qubit, right. So between bit and qubit. So as I know bit is either 0 and 1 and qubit, so bits are between 0 and 1, whereas qubits can have any combinations of 0 and 1 between any combinations. So therefore a bit will have two states available and you can have large number of, if not infinite, you will possibly have a large number of states available with qubits, right. Now the third point is, generally when you talk of bits you get the stored value, right. Now depending on the probability of occurrence of 0 and 1, you will either get a 0 or 1 as a qubit. You can copy a bit but you cannot copy a qubit in a perfect sense, and this is the problem, that when you try to access the qubit by an external source, the qubit itself changes its state. So, it becomes very difficult quantum mechanically to have a stable qubit state. For example, if I want to, it is something like this: I am seeing a person, or the light particles, photons which are hitting that person and coming back to my eyes, they are changing the state of the person. Then what I am seeing is not the person itself, but a modified state of the person. That is exactly what is happening in a qubit, right? It is very, very sensitive. And that comes to my fifth point here, and that is stability. Bits are highly stable. Why? Because bits can be either 0 1 with the presence of voltage or absence of voltage, whereas qubits are very, very sensitive to noise. A small amount of noise introduced in qubit will change the system drastically in most of the cases. Qubits are used in all classical computers, for example, which we know today, and all quantum computers which are in lab based quantum computers, we used qubits in that sense. So, there are two possible outcomes which are available with qubit, which is basically 0 or 1, right, and therefore, the state is binary. And the general state of qubit will be determined by quantum mechanics, right, and can be a coherent. If you apply principle of superposition, then it is basically a coherent superposition, a very nice word, a coherent superposition of all computable states simultaneously. So, basically what I am trying to say is that if you do a computational state, then all the possible computational states, a weight will be associated with it, and depending on the outcome, those weights will get changed, and you will get a exactly one value of output. But the number of possible outputs are very large in number, which is the second point I showed to you. Now, there is something that the word known as coherence in a qubit. Coherence basically means that if it is a high coherence system, it basically means that the two qubits are very coherent in the sense that you are not able to change its state by an external pulse, or by if you send a input signal to read the values of the qubits, if that changes this qubit state, then we define that to be as a slightly incoherent design in a sense, or incoherency is there. So, as I told to you, it is basically super dense coding of using 2 bits as such, right, and that is what it is always there. Now, let us come to the representation of a qubit, right. So, how the qubits are represented mathematically. As I told to you, classical state, we can represent classical state, let us say state number 1 as 0 and state number 2 as 1. So, there are 2 states available. So, as I discussed with you, if there are n bits available to me, then there are 2 to the power n states in a classical state. So, if there are n bits available, I will have 2 to the power n states, possible states, right, will be available for processor states, right. So, a quantum state can be a quantum state can be basically a superposition state of multiple occurrences, superposition states, which means that a qubit can have a non-zero probability in both its states simultaneously. Means I can have one state, another state, and one need not be 0 or the 1. The weight can be 0.5 of each, right, and that is possible. So, it is basically defined as non-zero probability, or a non-zero probability amplitude in a sense. Okay. Now, a qubit requires basically 2 complex numbers. It requires 2 complex numbers to describe 2 probabilities, right, and we define this to be as a quantum state vector, or we define to be as a superposition state vector, right. That is how you define a 2-dimensional so it is basically defined in 2-dimensional complex conjugate space as such. Okay. So, let me tell you therefore that in quantum mechanics, as I discussed here, we will come to this later on here, but let us look at a state. There are 2 states available to us. The first state is basically referred to as a 0 state, right. This is 0 state. There are 2 vectors, and these are 2 orthonormal vectors, right. These are also referred to as basis states and or basis vectors, and this is represented as with a matrix 1 0, and one vector state is referred to as 0 1, right. So, this is 0 1, and this is basically referred to as a bra or ket sort of. Those who are uninitiated to it, they are referred to as bra or ket notation, right, and therefore, they are referred to as ket 0. This is ket 0, this is ket 0, and this is ket 1, which you see. Okay. So, therefore, the 2, so let me rub this portion and therefore write down for you. So, what I can write down from here is that there will be 2 orthonormal basis states, and these are given by 0 and 1, and together they are 2-dimensional space, Hilbert space, they will be available. Now, if I write for, I will give an example. Let me write down 0 0 bra a cat. Then this will be also referred to as 0 0 will be 1 0 0 0, right. Similarly 0 1 will be, can be written 0 1 0 0, right. You can write down state 1 0, right, and is referred to as 0 0 1 0, and it is 1 1 state, then this is referred to as a 0 0 0 1 state, right. And they are referred to as n qubits, and by principle of superposition there are 2 to the power n dimensional Hilbert space. So, a pure qubit, right, is a coherent superposition of these basis states. These are the basis states, and these are the corresponding weights alpha and beta which you see, they are referred to as probability amplitude. They are referred to as probability amplitudes, and both are complex numbers, right. So, they are both complex numbers alpha and beta, and they are probability states, and they go on varying depending upon the probability of finding a 0 or 1 at a particular state. Now, a single qubit state will be therefore a superposition of ket 0 and ket 1 with multiplication of the probability amplitude alpha and beta, which is given as state 1 and state 2. Now, this is what we get, where alpha and beta is basically 1. Since alpha and beta are the probability density states, we will say that alpha square plus beta square will always be equals to 1, because the probability of finding the value is always equals to 1. That is how you define the outcome, right. And therefore, we say that, as I discussed with you, one state is given as 0 1, which you see here, right. Now, with this knowledge, we will be now going into deep dive into block sphere, but before that let me show to you in the Hilbert space how will I represent the value of the ket vectors in a sense. Okay, let's look at this diagram which you see in front of you. I am plotting, so I am trying to find out the alpha beta value, and this is 0 ket 1 0, and this is 1 ket 1 is 0 1. If I draw a line which is represented by this, and this is the point where I am trying to find out the value of the qubit, then it is given as eigenvalue will be, this is also referred to as an eigenvalue, right, is given as alpha ket 0 plus beta ket 1, right. And since 0 is given by 0 1, we break it down the 0 value to 1 0 and 1 to be equals to 0 1, and then if you multiply with this I get alpha beta, because this is alpha and this is beta. So, finally what I get from all this discussion is that the ket value is equals to alpha beta. So, I get a column vector of alpha beta, and this is also referred to as a Dirac notation, right, where alpha beta or ket value are given to you. So, what we have found out, take away from this discussion, is that whenever we have eigenfunction to be defined, it will be always a linear function of alpha and beta, such that alpha square plus beta square will always be equals to 1, and this gives me the probability of finding the particle at the probability of state of the particle in that sense of it, right. So, with this let me come to the usage of qubit, but before that maybe I can show you relevance and application, but before that let me explain to you the other aspects of qubit, right. Now, typically when we talk about qubits, we will also talk about a block sphere maybe in the later turn, but let me quickly go through the qubit usage. Now, typically when you do qubit manipulation or quantum computing manipulation, you first define the problem for sure, right, and therefore the first aspect is your problem definition. Problem definition can be any problem associated with any logic or otherwise problem, right. Then we design the algorithm, right. So, algorithm design is the next stage which we do. Then we use some coding languages, right, and these coding languages are basically code development programming can be done here. It is almost like a conventional compiler design, but then here it is something slightly different as compared to a conventional one in case of quantum qubits. After we have compiled it, we generally do a hardware emulation. In our digital logic, we use, for example, FPGAs for emulation purposes. Here we do something else to do it. And what we do is that we therefore replace so for example, a quantum processor by a standalone logic processor by a quantum processor here, and we get either in the output in the console we get, and therefore the solution is achieved. So, this is the typical flow of the data, or the typical flow of the data across the qubit usage in a sense, right. Okay. And therefore, what the whole idea is that when you do, for example, when you do a logic design, you first define a problem statement, you do an algorithm design, then you do the coding language. The coding language is either Verilog, A or VHDL. Algorithm design can be even as simple as k mapped, you need to do it, and there you will have some logic, and then you will be a compiler. Compiler will help you in this case. For example, the corresponding analog to digital is basically designing it via gates, and then you will be doing it in a hardware emulation where lookup table, flip flops, how many if you are doing a sequential design, so on and so forth. So basically the quantum, in this case the quantum gates will be replacing the logic gates. You see, quantum gates will replace all the logic gates as such. Okay. And the CPUs will run binary logic, for example AND, OR, NOT, XOR gate logic will be there, right. The logic gates will therefore, using the logic gates I can build a control unit, ALU and data path. It is almost the same as your standard logic design, and we use all additions, comparisons using gate level circuitry, right. So these are the few areas in which qubit usage is there and has been there for quite a long time. This is the qubit usage area. Now let us look at how the qubits are built, right. So basically I want to look qubits into a state, it is basically a state, right. A state can be given by either 0 or a 1. The way we see the qubits are, there are 2 or 3 multiple ways of looking at it. One is using superconducting qubits or using electron spin qubits, spintronics, and so on and so forth. So for example, if I say that this electron is spinning in the clockwise direction, let us suppose, then we define, let us suppose, its state to be is equals to its corresponding your corresponding polarization state is plus 1 by 2, and if it is a reverse spin it is minus 1 by 2. So if it is a clockwise rotation, I will define it by say ket 0 state, and if it is an anti-clockwise we will refer to as a ket 1 state, right. Similarly, if you look at quantum dots, non-volatile centers in diamond, that is also one of the examples. So as long as you are able to distinguish between 2 states by certain parameters of that state, we will be happy in terms of having the qubits built. Then another is the photon polarization, right. So if it is a horizontal polarization or a vertical polarization, that will also encode the qubit states, right. So if I say it is a horizontally polarized, we define that to be as a state ket 0, and if it is vertically polarized as ket 1 state. Okay. Why optical quantum computing is important? For all fiber optic based optical communication, quantum communication, we might use the horizontal and vertically polarized quantum states available to us. Let us look at the superconducting loops, and these are also referred to as Josephson junctions, and this is basically superposition of direct current, right, current direction. So it is basically clockwise or anti-clockwise, and IBM Quantum and Google Sycamore have used such superposition of current design known as Josephson junction to do it. And typically if you look across the board, these are all done at very low temperature, and that is the reason I told you that the very fact that these are used in designing of cryogenic electronics for quantum computing, the reason is that at such a low temperature the states are almost fixed in its position, and since there are no thermal changes taking place, the switching of the states will not take automatically until and unless you force it from an external source, and that is the reason everything is actually done at a cryogenic instance of time. Okay, let us come to the application and relevance. I will not go into details of individual of them, this is just a flow chart to show to you. Basically one important point is one of the important ideas or one of the important dimensions of this structure is that its key cannot be broken by any computer, right. As of now there are quantum keying is very stable and not only stable, it is very robust as well. Then it cannot be intercepted. So once you try to intercept it, you change the state, right, and that makes the detection almost sort of not possible in a sense. So what we do is, so if you look at the first diagram here, this is a basic diagram of a quantum cryptographical procedure, right, and what we do is that we have a plain text here. Plain text basically means a 1 or a 0 state in a proper sense, and then what we do is that somewhere in the middle we do an encryption here. So we do have the plain text here, and this is my encryption here. We add the encryption by an external keying device, for example a quantum key distribution state here. This is through internet and mobile phone we send the ciphered key here, text here, and then we at the receiver end we do a decryption. So we encrypt here the message here, add some extra bits here such that the original message is sort of hidden, and somewhere here we try to decrypt it by the same dekeying key, and we get the plain text output in the output side, right. Now the key distribution between the encryptor and decryptor is done by a photon, and at the photon level, if you want to actually check the state of the photon state actually changes drastically, and therefore you will never be able to get the key with you. It is something like this, that if you have a key with you, you lock the door of your house and you go away, and then what you do is that you carry the key, but if somebody wants to watch the key hypothetically, and he wants to take the key from you physically, the key's pattern will change automatically, and therefore even if it reaches him, he or she won't be able to open the door even in your absence, right. And that is the reason it is almost analogous to a design which you see in case of a proper encrypting and decryption key in case of quantum mechanics. And therefore let us come to why we require quantum computing. Well, obviously new problems can be solved, right. That is the major one play. And if you have seen many reports where quantum computing is actually being achieved to solve a big problem within, let us suppose within few hours it is able to solve, which was possibly taking years for classical computers to solve it, right. For example, and it goes beyond electronics, it goes beyond the applications of electronics. It can even be going for big data, for example in pharmaceutical places where you do molecular simulation to find out the various structures available to us. There are a large number of combinations of structure available. Which structure will be the most suitable one can be done very fast. Similarly, another area where people are looking into is basically for new material and trying to find out the new materials sort of influence on the quantum computing. And so second one is basically important, that new materials can be found out. And the third one is since qubits can represent many states at one point of time, there is a potential of massive scale up in the tasks, and that is the reason we define that to be as a strong parallelism inserted, right. So qubits basically represents many states at once, and there is a potential for massive speed ups, right. Why? Because you are doing parallelism. Why parallelism? Because states can be any qubits can be represented by represents many state at same instant of time. So you have multiple states available, and each state has got a probability, and therefore I will have a strong parallelism available to us. Then many new and unexplored systems can be evaluated using the quantum computing, right. Then drug discovery, there is optimization problem, new material sources, stable material sources in material engineering and solid state engineering. Then we have cryptographic and quantum physics simulations are the areas where there is a large number of quantum computing people are working on. Why? Because since now, as you all are aware of, that the Moore's law is slowing down, we basically need a new paradigm in quantum computing, and therefore we require to have a stronger computer which deals very fast with all these paradigms. So that is the reason quantum computing is essentially very important in order to handle such ideas. So we can understand what is the motivation for quantum computing coming up in a big way is all the ones which I have stated above. Please keep in mind that all these states have to be stable, have to be highly coherent, and that is the reason you try to do that or apply that in very low temperature at cryogenic temperature, right. And that is the major idea what we are trying to do. Okay, so let me recapitulate what we did in this lecture. We tried to give you a brief idea about quantum computing, what is it meaning of quantum computing, what is the meaning of states of quantum computer, what is the meaning of ket 0 and ket 1, and each state can be represented by a column matrix. And we also saw that the overall value of alpha and beta can be represented as 1 alpha. So basically if the way I was discussing with you was something like this. If you have, when you represent an eigenfunction, you represent the psi value as a column matrix of alpha and beta. Alpha and beta have multiple values depending upon the states which you get, right. And this gives you quite a substantial idea about the quantum computing. We then finally ended up our discussion with the applications of quantum computing which we are looking into. With this we end this lecture. I hope you enjoyed the lecture. Till we meet next time, goodbye.